Hello, Midnight Wanderer. Yes, you. The one who's found their way here in the quiet hours. The one who looks up sometimes when the world grows still and wonders. Welcome to the Midnight Explorer. Tonight, we're going somewhere ancient. Somewhere that exists both impossibly far away and right here in this very moment. We're going to a place that every human who has ever lived has known, yet never truly touched. Tonight, we're going to the stars. But not the stars you might expect, not the scientific diagrams or the cold mathematics, though those have their beauty too. No, tonight we're going to discover the stars as they were first discovered, through wonder, through fear, through hope, through the trembling realization that we are small, and yet somehow, mysteriously, we matter. So find yourself somewhere comfortable. Let the weight of the day begin to lift from your shoulders. Take a breath, deep and slow, and let yourself settle into this moment, this story, this ancient relationship between earth and sky. Are you ready? Then let us begin, as all star stories must, with darkness. Imagine, if you will, a night 300,000 years ago. The sun has set on the African savanna. The air, which was scorching just hours before, now carries a coolness that makes the skin prickle. Somewhere in the distance, a hyena laughs. That strange, unsettling sound that seems half human, half nightmare. And there, huddled around a small fire, is a group of our ancestors, not quite us, not yet fully human in the way we think of it now, but human enough to feel fear, human enough to wonder, human enough to look up. One of them does, a young woman perhaps, or a child. The details are lost to time, but the moment isn't. Because in that moment, when the eyes lifted from the fire to the darkness beyond, something happened that had been happening for billions of years, but had never until then been witnessed with consciousness. The stars were looking back. Imagine seeing them for the first time, not as we see them now, filtered through light pollution and smartphone screens and the casual familiarity of 1,000 nights, but truly for the first time. Every point of light a mystery, every constellation an unread story. The Milky Way, that river of light we can barely see now from our cities, stretching across the entire dome of the sky like a road made of crushed diamonds. What did she think, that first conscious observer? Did she think there were holes in the sky letting through light from some realm beyond? Did she think they were the campfires of ancestors? Did she think they were the eyes of gods watching? Or did she simply feel what you might feel if you took the time to really look up on a clear night? A strange mixture of insignificance and importance, of loneliness and connection, of fear and comfort, all at once. The stars have always done this to us. They've always made us feel small and grand simultaneously. They've always been a mirror in which we see not just ourselves, but our questions. Where do we come from? Where are we going? Are we alone? These questions, whispered in 1,000 languages across 10,000 generations, all began with that simple act, looking up. Let's stay in this deep past a moment longer. Let's walk forward through time, but slowly, gently, as the stars wheel overhead. The seasons change, the centuries pass, the millennia unfold like the petals of an impossibly slow flower. And everywhere humans go, and we go everywhere, don't we? We take the stars with us, not physically, of course, but in our minds, in our stories, in our attempts to make sense of this bewildering existence. In ancient Mesopotamia, the priests climb ziggurats to be closer to the stars. They begin to notice patterns. That bright one there, we'll call it Venus, appears in the evening, then disappears, then appears in the morning. It follows a pattern. It's predictable. And if it's predictable, perhaps it means something. Perhaps it can tell us when to plant crops, when to expect floods, when to prepare for war. The stars become a calendar, a clock, a warning system. But they're also something more. In Egypt, the star we call Sirius rises just before the sun during the time when the Nile floods. Every year, like clockwork, this bright blue-white point of light appears on the horizon just before dawn, and within days, the river that is Egypt's lifeblood begins to swell. Coincidence? To the ancient Egyptians, this was no coincidence. This was the goddess Sopdet announcing the new year. This was the universe speaking in the language of light. In China, astronomers keep meticulous records. They note when new stars appear, what we now call supernovae, the explosive deaths of massive stars. They write these observations on oracle bones, on bamboo strips, in texts that will survive thousands of years. They don't know what they're seeing, not really, but they know it's important. They know the sky is not unchanging, not static. The sky is alive. In Greece, they begin to do something revolutionary. They begin to ask not just what, but why? Not just when will the stars appear, but what are they made of? How far away are they? Do they move, or do we? A man named Aristarchus proposes something outrageous. Perhaps the Earth moves around the sun, not the other way around. Perhaps the stars only seem to move because we're the ones in motion. He's ridiculed. The idea is too strange, too contrary to common sense. The Earth feels solid, unmoving. Surely it's the sky that turns. But the seed is planted. The question is asked. And once a question is truly asked, it can never quite be unasked. There's something we need to understand about the stars. Something that's easy to forget in our age of scientific understanding. For most of human history, the stars weren't just objects. They were stories. They were gods. They were fate itself. Let me take you to ancient Greece again, but this time let's sit with the shepherds on the hillsides. Let's feel the cool night air and smell the wild thyme. Let's watch as an old man points upward, teaching a young boy the stories written in light. You see those 7 stars there, he says, pointing to a cluster we now call the Pleiades? Those are sisters, 7 sisters who were pursued by Orion, the great hunter. They begged the gods for protection, and Zeus transformed them into doves, and then into stars. But Orion still chases them across the sky, night after night, never catching them, never giving up. The boy listens, memorizing not just the position of the stars, but the story, the meaning, the way these points of light connect into narrative. This is happening everywhere, in every culture, in every age. The stars aren't just observed, they're interpreted. They're woven into the fabric of meaning that makes life bearable. In Aboriginal Australia, the dark patches in the Milky Way are as important as the bright stars. They see an emu in the sky, its body formed by the dust clouds that block the light. The emu is a sacred story, a map, a seasonal calendar, a connection to the dreaming, that eternal now where past, present, and future exist simultaneously. In Norse mythology, the stars are sparks from the forge of creation, or the eyes of those who died in battle, watching over their descendants. The Milky Way is the path that souls travel to reach Valhalla. In India, the stars are the gods themselves, or their jewels, or the reflections of an infinite cosmic dance. In Polynesia, the stars are a navigation system so sophisticated that it allows voyagers to cross thousands of miles of open ocean without instruments, guided only by the positions of stars, the patterns of waves, the flights of birds, the color of clouds at dawn. Every culture looks up and sees not just light, but meaning. This is not primitive thinking. This is not ignorance. This is the human mind doing what it does best, making connections, finding patterns, creating stories that bind us to the cosmos and to each other. Because here's a relaxing fact about stars, a true one that might help you sleep tonight. Every atom in your body was formed inside a star. It's not poetry. That's physics. The hydrogen in your water, the calcium in your bones, the iron in your blood, the carbon in your DNA, all of it, every single atom heavier than hydrogen and helium, was forged in the nuclear furnace at the heart of a star, or in the cataclysmic explosion when that star died. You are, quite literally, made of stardust. Which means those ancient stories weren't entirely wrong. We are connected to the stars. Not because they determine our fate, perhaps, but because we share a common origin. We're family, in the deepest possible sense. Here's another night in 1054 CE. On July 4th of that year, Chinese astronomers recorded the appearance of a guest star in the constellation Taurus. It was bright enough to be seen in daylight. It remained visible for 23 days in the daytime and 653 days in the night sky. We know now what they were seeing: a supernova, the explosive death of a massive star about 6,500 light-years from Earth. The explosion released more energy in a few weeks than our sun will emit in its entire 10-billion-year lifetime. The remnant of that explosion is still visible today. We call it the Crab Nebula. It's an expanding cloud of gas and dust, glowing with the fierce energy of that ancient cataclysm, spinning around a neutron star, the collapsed core of the original star that rotates 30 times per second. But in 1054, the Chinese astronomers didn't know any of this. They simply recorded what they saw: a new star, brighter than Venus, hanging in the sky like a cosmic exclamation point. Was it an omen? A message from heaven? A warning or a blessing? We don't know what they thought. We only know they watched, and they recorded, and they preserved that observation for us across nearly 1,000 years. This is one of the gifts the stars have given us: perspective. Not just the perspective of physical distance, although that's staggering enough, but temporal perspective, the perspective of deep time. When you look at the Crab Nebula today through a telescope or in a photograph, you're seeing light that left that stellar explosion almost 1,000 years ago. You're seeing the past directly, Not a memory or a recording or a story, but the actual light from the actual event traveling across space at 186,000 miles per second for century after century, until it finally reaches your eye. The star that died to create the Crab Nebula died around 5500 BCE, before writing was invented, before the pyramids were built, before agriculture spread beyond its birthplace in the Fertile Crescent. And yet we can see it. We can see its death throes still playing out in the sky. This is the strange temporal elasticity of starlight. The stars teach us that now is not quite as simple as it seems. The universe doesn't have a single present moment. It has layers of past, present, and future all existing simultaneously depending on where you are and how fast you're moving and what you're looking at. Isn't that relaxing in a way? The pressure of the present moment, the anxiety of what's happening right now, it's not quite as absolute as it feels. Time is softer than we think, more flexible, more forgiving. Let's jump forward now, not too far, just to the 16th and 17th centuries, to a time when the old stories about stars were beginning to crack open, revealing something even stranger inside. Let's meet a man named Tycho Brahe. Tycho is a Danish nobleman with a golden prosthetic nose. He lost the real one in a duel over a mathematical dispute, which tells you something about both his personality and his times. He's obsessed with the stars, not with the stories about them, but with their precise positions. Where exactly are they? Do they move? By how much? On November 11, 1572, Tycho is walking home when he notices something impossible. There's a new star in the constellation Cassiopeia. Bright, brilliant, definitely not there before. This shouldn't be possible. According to Aristotle, according to nearly 2,000 years of accepted wisdom, the heavens are perfect and unchanging. The realm beyond the moon is eternal, crystalline, divine. Stars don't just appear. But there it is. Tycho begins to observe it obsessively. He measures its position night after night, checking for parallax, the apparent shift in position that nearby objects show when viewed from different angles. If the new star were close, between Earth and the Moon, it would show parallax as Earth moved in its orbit. It shows no parallax, which means it's far away, very far away, which means it's not a nearby phenomenon in Earth's atmosphere or even in the imperfect realm below the Moon. It's in the realm of the stars themselves. The heavens, Tycho realizes, are not unchanging. The stars are not eternal and fixed. The universe can surprise us. We know now that Tycho had witnessed a Type 1a supernova, a type of nuclear explosion that occurs when a white dwarf star accretes enough matter from a companion star to trigger runaway nuclear fusion. But Tycho didn't know this. He just knew the universe had revealed itself to be more dynamic, more alive than anyone had thought. Tycho builds an observatory on the island of Hen. He calls it Uraniborg, Heaven Castle. For 20 years, he makes the most precise astronomical observations ever attempted, without a telescope, just with quadrants and sextants and an almost superhuman attention to detail. He measures the positions of 777 stars with unprecedented accuracy. He tracks the planets night after night. He accumulates data. He doesn't understand it all. He can't quite bring himself to accept the Copernican model, that the Earth orbits the Sun. It's too strange, too uncomfortable. So he creates his own model. The Sun and Moon orbit the Earth, but the other planets orbit the Sun. It's a compromise between the old and the new. It's also wrong. But that doesn't matter. Because what Tycho does is provide the raw material, the measurements, the data, the precise observations that will allow the next generation to figure it out. There's a gentle transition. The music becomes slightly more hopeful. Enter Johannes Kepler. Kepler is Tycho's assistant, and later his successor. He inherits Tycho's data, and he has something Tycho lacked: a willingness to accept whatever the data says, no matter how strange. Kepler is also deeply mystical. He believes in the harmony of the spheres, the idea that the universe follows musical and geometric principles. He's trying to understand the mind of God as expressed in the movements of the planets. He's struggling with Mars. The planet won't behave. Its orbit doesn't fit any of the perfect circles that everyone assumes celestial motions must follow. He tries circle after circle, adjustment after adjustment. Nothing works. The data, Tycho's precious precise data, keeps disagreeing with his models by just a tiny amount. 8 minutes of arc, 1/8 of a degree. Many astronomers would have ignored such a small discrepancy, blamed it on measurement error, adjusted the theory slightly, and moved on. Kepler doesn't. He later writes, "Out of these 8 minutes, we will construct a new theory that explains the movements of all the planets." And he does. He throws away circles. He tries ellipses. And suddenly, magically, everything works. The orbits of the planets are not perfect circles, but ellipses, with the sun at one focus. And they follow precise mathematical laws, laws that Kepler discovers and formulates. These laws will later allow Isaac Newton to formulate his law of universal gravitation. They'll allow Edmund Halley to predict the return of the comet that now bears his name. They'll eventually allow us to navigate spacecraft to other planets, to calculate the orbits of exoplanets around distant stars, to understand the dynamics of entire galaxies. All because Kepler took those 8 minutes of arc seriously. All because he insisted that reality, however strange, matters more than our assumptions about what reality should be. Here's a relaxing fact. The stars don't care about our theories. They just do what they do, following the laws of physics with perfect consistency, indifferent to whether we understand them or not. There's something comforting about that. The universe isn't trying to trick us or test us. It's not malicious or capricious. It simply is what it is, and if we pay attention, if we measure carefully, if we're willing to be surprised, it will teach us. The music continues, perhaps adding a very soft high melody like a distant flute. Let's talk about distance now. Because one of the most profound questions humans have asked about stars is simply, how far away are they? They look close. The ancient Greeks thought they might be just beyond the sphere that carries the planets, maybe a few million miles away. But they're not. They're so much farther than that. In 1838, a German astronomer named Friedrich Wilhelm Bessel finally measures the distance to a star, 61 Cygni, using parallax. Real parallax, not just the lack of parallax that Tycho observed, but the tiny, tiny shift in position that a star shows when viewed from opposite sides of Earth's orbit around the Sun. The star shifts by less than 1 arcsecond, 1/3600th of a degree. From that minuscule shift, Bessel calculates the distance, about 11 light years. 11 years traveling at the speed of light. That's how long the light from that star takes to reach us. To put that in perspective, if you could travel at the speed of a commercial jet, it would take you about 17 million years to reach 61 Cygni. And that's one of our near neighbors. The nearest star visible to the naked eye is Alpha Centauri, about 4.4 light years away. The center of our galaxy is about 27,000 light-years away. When you look at Andromeda in the night sky, if you can find it, if you're far enough from city lights, it looks like a small fuzzy patch. You're looking at light that began its journey before humans existed in our current form. You're looking back across more than 2 million years of time. The stars teach us about scale, about the vastness of space and time, about how small we are in one sense and how remarkable in another. Because we're small, we're tiny. We exist on a small rocky world orbiting an average star in the suburbs of an ordinary galaxy in an observable universe that contains hundreds of billions of galaxies. But we're the ones asking the questions. We're the ones measuring the distances. We're the ones figuring it out. The universe is vast and old and powerful, yes, but it's also, as far as we know, mostly unconscious. Mostly just matter and energy following physical laws. We're the consciousness. We're the part of the universe that woke up and started wondering about itself. That's not small. That's miraculous. Let me tell you about a discovery that changed everything. In 1814, a German optician named Joseph von Fraunhofer was studying sunlight through a prism, separating the white light into its component rainbow of colors, when he noticed something strange. The spectrum wasn't continuous. It had dark lines in it, hundreds of them, thin, dark bands at very specific wavelengths. What were these lines? For decades, no one knew. They were just a curiosity, the Fraunhofer lines. Then, in the 1850s and 60s, physicists began to realize something extraordinary. When you heat different chemical elements until they glow, each element produces light at very specific wavelengths. Sodium always produces light at certain wavelengths, hydrogen at others, iron at others. And when light passes through a cool gas of those same elements, they absorb light at exactly those same wavelengths, creating dark lines in the spectrum. Do you see what this means? The dark lines in the sun's spectrum are absorption lines. They're telling us what elements are present in the sun's atmosphere. We can read the sun's composition in the language of light. And if we can do it for the sun, we can do it for any star. Suddenly, the stars aren't just distant points of light. They're objects we can analyze. We can determine their temperature, their chemical composition, their motion toward or away from us by the Doppler shift of the spectral lines, even their magnetic fields. The stars become knowable. A woman named Annie Jump Cannon, working at the Harvard College Observatory in the early 20th century, classifies the spectra of hundreds of thousands of stars. She develops a system, OBAFGKM, that organizes stars by temperature and composition. Generations of astronomy students will memorize this sequence with the mnemonic, "Oh, be a fine girl, kiss me," although that's now often updated to gender-neutral versions. Cannon works with incredible speed and accuracy, classifying stars faster than anyone thought possible. She'll eventually classify over 350,000 stars in her career. She's deaf. She's a woman in an era when women weren't supposed to be scientists. She works at a desk in an observatory where she's not even allowed to use the telescopes, and yet she maps the diversity of the stars with unprecedented thoroughness. Another woman, Henrietta Swan Leavitt, makes a discovery even more profound. She's studying variable stars, stars that change in brightness over time, in the Magellanic Clouds, two small satellite galaxies visible from the southern hemisphere. She notices a pattern. The brighter a certain type of variable star, called Cepheid variables, is intrinsically, the longer its period of variation. The relationship is precise, consistent.
This is huge. If you know a star's period, you can calculate its intrinsic brightness. And if you know its intrinsic brightness and you can measure its apparent brightness, you can calculate its distance. Leavitt has discovered a cosmic yardstick, a way to measure distances, not just to nearby stars, but to entire galaxies. This discovery will allow Edwin Hubble, a decade later, to prove that the spiral nebulae are actually distant galaxies outside our Milky Way. It will allow him to discover that the universe is expanding. It will be foundational to our understanding of the size and age of the universe. Henrietta Leavitt never gets much recognition in her lifetime. She works as a computer. That's what they called the women, almost always women who did astronomical calculations by hand. She's paid less than the men. Her work is published under her male supervisor's name. But her discovery echoes through the decades. It helps reveal the true scale of the cosmos. Here's something that might help you rest tonight. The stars are telling us their stories constantly. All we have to do is listen. Every photon of starlight that reaches your eye has been on a journey. It was born in the core of a star, produced by nuclear fusion when hydrogen atoms slammed together under immense pressure and heat to form helium. That process released energy, light. But the photon couldn't escape immediately. The core of a star is incredibly dense. The photon would travel a tiny distance, then be absorbed by an atom and re-emitted in a random direction, absorbed again, emitted again, bouncing around like a pinball machine in the densest pinball machine imaginable. For a photon born in the core of the sun, this random walk through the sun's interior takes on average between 100,000 and 150,000 years. Let that sink in for a moment. The light you see from the sun, the warmth on your face, the glow of a sunset, the gleam off the ocean, that light is ancient. It was born in nuclear fire before your species existed, when mammoths walked the earth, when the last ice age was still thousands of years in the future. Then finally, the photon reaches the surface. It escapes into space, and then, for 8 minutes, it travels unimpeded across 93 million miles of emptiness until it reaches Earth, passes through our atmosphere, and enters your eye. In your retina, it's absorbed by a molecule called rhodopsin. That absorption triggers a cascade of chemical reactions that creates an electrical signal in your optic nerve. Your brain interprets that signal as light, as vision, as the sun. The universe has touched you, directly, physically. A thing that was born in nuclear fire before your species existed has traveled across space and time to interact with the molecules in your eye. This is happening right now, all the time, with every star you see. You're connected to them, touched by them, receiving messages written in light. And here's the thing. The stars don't know you're watching. They don't know you exist. They're not trying to communicate. They're just being stars, doing what stars do. But you're here, conscious, aware, able to understand, even a little, what you're seeing. That's the miracle. Not that the stars exist, but that you exist to see them. Let's talk about what stars actually are. Not metaphorically, not poetically, but physically, in a way that's so strange and beautiful that it circles back around to poetry anyway. A star is a ball of mostly hydrogen gas, collapsed under its own gravity until the core becomes so hot and so dense that hydrogen nuclei overcome their natural repulsion and fuse together. 4 hydrogen nuclei, 4 protons, through a series of reactions, become 1 helium nucleus, 2 protons and 2 neutrons. The helium weighs slightly less than the 4 hydrogens did. That missing mass has been converted to energy according to Einstein's famous equation, E equals mc squared. A tiny amount of mass, the speed of light squared. That's a lot of energy. For every kilogram of hydrogen that fuses into helium, the sun converts about 0.7% of that mass, 0.007 kilograms, into pure energy. It does this 600 million tons at a time, every second. And this has been happening for 4.6 billion years. And it will continue happening for another 5 billion years. The sun is patient. The sun is steady. The sun is reliable in a way that almost nothing else in our lives is reliable. Every day of your life, the sun has risen. Every day of your ancestors' lives, going back millions of years, the sun has risen. Every day of your descendants' lives, for generations beyond counting, the sun will rise. Isn't that comforting? The sun doesn't depend on politics or economics or human drama. It doesn't care about your mistakes or your victories. It simply shines, as it has shown, as it will shine, following the inexorable laws of nuclear physics and stellar evolution. You can count on it, literally. It's the most reliable thing in your life. Music continues its gentle progression. But stars don't live forever. They can't. The hydrogen runs out eventually. The fusion reactions that hold a star up against its own gravity begin to falter. What happens next depends on the star's mass. For stars like our sun, medium-sized, stable, ordinary stars, the end is relatively gentle. When the hydrogen in the core runs out, the core contracts and heats up. Hydrogen in a shell around the core begins fusing. The outer layers expand. The star becomes a red giant, cool but luminous, so large that it might swallow the inner planets. Our sun will do this in about 5 billion years. Earth might survive. Orbital dynamics are complex, but if it does, it will be a scorched, lifeless cinder. Eventually, the red giant sheds its outer layers in a stellar wind, creating a beautiful planetary nebula, shells of glowing gas expanding into space. The core, no longer producing energy, contracts into a white dwarf, a star-sized piece of matter compressed to about the size of Earth, with a density so extreme that a teaspoon would weigh as much as an elephant. This is a white dwarf, and it's cooled slowly, over trillions of years, eventually becoming a black dwarf, a cold, dark ember of a once-living star. The universe isn't old enough yet for any black dwarfs to exist. Even the oldest white dwarfs are still glowing faintly. But given enough time, trillions upon trillions of years, this is the fate of most stars: to become cold, dark, dense remnants drifting through an ever-expanding space. But for massive stars, stars more than about 8 times the sun's mass, the end is more dramatic. These stars live fast and die young. They burn through their hydrogen in just millions of years instead of billions. And when the hydrogen runs out, they don't just fade away. They keep fusing. Helium into carbon and oxygen, carbon into neon and magnesium, neon into oxygen and silicon, silicon into iron. Each stage produces less energy and lasts for a shorter time. A star might fuse hydrogen for millions of years, helium for thousands, silicon for a single day. And then it hits a wall. Iron. Iron is the most stable nucleus. You can't extract energy by fusing it into something heavier. You can't extract energy by splitting it into something lighter. Iron is the end of the line. So the core of the star, now made of iron, stops producing energy. Nothing holds it up against gravity anymore. In less than a second, it collapses. The core, which was roughly the size of Earth, contracts to a sphere about 30 kilometers across.
Protons and electrons are crushed together to form neutrons. The density becomes so extreme that a teaspoon of the material would weigh as much as Mount Everest. This is a neutron star, and it's supported not by pressure but by the quantum mechanical principle that no two neutrons can occupy the same quantum state. It's held up by the stubbornness of the Pauli exclusion principle. But the collapse doesn't happen smoothly. It happens so fast that it creates a shock wave, a rebound that blasts outward through the outer layers of the star. The star explodes. This is a core collapse supernova. For a few weeks, a single star can outshine an entire galaxy of hundreds of billions of stars. And in that explosion, in that moment of cataclysmic violence, something miraculous happens. The elements heavier than iron, elements that can't be formed by normal fusion because they'd require energy input rather than releasing energy, are formed. Gold, silver, platinum, uranium, all the heavy elements in the universe were formed in the fiery deaths of massive stars or in the collisions of neutron stars. The gold in your jewelry, if you wear any, the uranium in nuclear reactors, the iodine in your thyroid, all of it was forged in stellar explosions. You're wearing, carrying, literally made of the remnants of dead stars. Music swells very slightly, still gentle, but with a sense of majesty. Here's a relaxing thought. You are the universe experiencing itself. Those atoms in your body, the ones formed in stars, they were scattered into space by supernovae. They became part of nebula, great clouds of gas and dust drifting between the stars. Slowly, over millions of years, gravity began to pull these clouds together. Some regions became denser. The denser regions attracted more matter. Eventually, new stars formed. Planets formed. Our sun, our Earth, you. The atoms in your left hand and the atoms in your right hand probably came from different stars at different times in different places. You're a collection, an assembly, a temporary gathering of stardust that has somehow become conscious, somehow become able to think and feel and wonder. And here's the thing, this isn't special to you. It's true for every person you've ever met, every tree you've ever seen, every animal, every plant, every bacterium. We're all stardust. We're all nuclear waste from the cosmic alchemy of stellar fusion and stellar death. But we're alive. We're aware. We're the part of the cosmos that woke up. Carl Sagan said it beautifully. The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. When you look up at the stars, you're not just looking at something foreign and distant. You're looking at your ancestors, your origins, your kin. The iron in your blood was forged in a star that died before the sun was born. The calcium in your bones was formed in a supernova billions of years ago. The oxygen you breathe was created in the core of a massive star and scattered into space when that star exploded. Every breath you take is an act of cosmic recycling. Every heartbeat moves atoms that have existed for billions of years through pathways that have existed for decades. You're old and young simultaneously. Made of ancient matter arranged in a temporary pattern called you. Doesn't they put things in perspective? The worries that keep you up at night, the anxieties that gnaw at you, they're real, they matter, they're valid, but they're also temporary, ephemeral, brief disturbances in the long, slow dance of matter and energy. The atoms will persist. They'll outlast your worries. They'll outlast you. Eventually, they'll become part of something else, other people, other living things. Perhaps billions of years from now, part of other worlds. You're a moment
in the life of stardust. But what a moment! What an unlikely, beautiful, conscious moment! Let's talk about something that might seem impossible. Stars dance. Not metaphorically, not in some poetic sense. They actually move in patterns, in rhythms, in relationships with each other that can only be described as choreography. Most stars, perhaps half of all stars in our galaxy, exist in binary systems or multiple star systems. They're not alone. They have partners. Imagine two stars orbiting each other, bound by gravity. One might be larger, brighter, more massive. The other smaller, dimmer, following its companion through space. They circle their common center of mass, not the center of the larger star, but a point somewhere between them, weighted by their respective masses. If the stars are similar in size, this point lies roughly between them, and they perform an elegant waltz, each tracing its own path through space, never touching, always together. If one star is much more massive than the other, the center of mass lies closer to the larger star, perhaps even inside it. The smaller star seems to orbit the larger one, but really, both are orbiting their mutual center of gravity. The larger star wobbles slightly as the smaller one circles. This dance has been going on for millions or billions of years. It will continue for millions or billions more. They're faithful to each other, these binary stars, bound by gravity, which may be the most reliable form of commitment in the universe. Gravity doesn't forget. It doesn't grow tired. It simply is, and so the dance continues. In the constellation Cygnus, the Swan, there's a binary system called Cygnus X1. One of the stars is an ordinary blue supergiant. The other is invisible. But we know it's there. We can see the supergiant wobbling, pulled by something we can't see. We can see material being pulled off the supergiant, spiraling inward toward its invisible companion, heating up as it accelerates, glowing in X-rays. The invisible companion is a black hole. The first black hole ever identified with certainty. Even black holes, those most alien of objects, those regions of space-time so warped that not even light can escape, even they participate in the dance. Even they have partners. The supergiant and its black hole companion orbit each other every 5.6 days. They've been doing this for millions of years. They'll continue until the supergiant itself dies, perhaps exploding as a supernova, perhaps collapsing to form a second black hole, and then two black holes will dance together, spiraling slowly inward over millions or billions of years until they finally merge in a cataclysm that releases more energy in a fraction of a second than the sun will emit in its entire lifetime. When black holes merge, they create ripples in space-time itself, gravitational waves that propagate outward at the speed of light, stretching and compressing space as they pass. We've detected these waves. We've heard the song of merging black holes, translated into sound. The universe is singing to us. All we had to do was learn how to listen. Let me tell you about a place called the Trapezium. In the constellation Orion, the Hunter, one of the most recognizable patterns in the night sky, there's a fuzzy patch visible to the naked eye. It's the Orion Nebula, a stellar nursery, a place where new stars are being born. At the heart of the Orion Nebula, there's a cluster of 4 bright stars called the Trapezium. These stars are young, less than 1 million years old, babies by stellar standards. They're hot, massive, and brilliant, and their intense ultraviolet radiation is causing the surrounding gas to glow. But the trapezium isn't just 4 stars. It's part of a larger cluster of thousands of young stars, all born from the same cloud of gas and dust, all siblings in the truest sense. And they're moving, not randomly, but in a coordinated way, like a flock of birds or a school of fish. They share a common motion through space, a legacy of the rotation of the original gas cloud from which they formed. Someday, millions of years from now, this cluster will disperse. The stars will drift apart, their shared motion gradually overcome by the gravitational influences of other objects in the galaxy. They'll become strangers to each other, scattered across the galaxy with no obvious connection. But they'll always be siblings, always share that common origin. The elements in their cores, the rhythms of their lives, the fundamental nature of their being, all of it traces back to that single cloud of gas, that single moment of collapse and fragmentation and star formation. Family in the deepest sense, not by choice but by origin, not by proximity but by shared history. Doesn't it make you think about your own origins, your own siblings if you have them, your own connection to people who share your history even if you've drifted apart? The universe is teaching us something here. Connection isn't just about physical closeness. It's about shared origin, shared substance, shared story. Here's a fact that might help you sleep. The stars in the night sky are moving, but so slowly from our perspective that the constellations would look essentially the same to your great-great-great-grandchildren. We think of the stars as fixed stars, the ancient astronomers called them, to distinguish them from the wandering stars, the planets. But they're not fixed. They're moving, all of them, at speeds of tens or hundreds of kilometers per second. They orbit the center of the galaxy, taking about 225 million years to complete one orbit. Some move faster than the galactic average, some slower, some are headed toward us, some away. But they're so far away that this motion is almost imperceptible. The constellation Orion looked essentially the same to the ancient Egyptians as it does to us. It will look essentially the same to people 10,000 years from now. There's something deeply comforting about that stability. The sky your ancestors looked up at is the same sky you see. The patterns they traced, the stories they told, the meaning they found, you can still access that. You can still share in that human experience that stretches back thousands of years. Your descendants, if you have any, will look up at essentially the same sky. They'll see Orion the hunter, Ursa Major the great bear, Scorpius the scorpion. The sky is a shared heritage, a common inheritance across all of human history. We're all under the same stars, always have been, always will be, at least for the foreseeable human future. That's stability. That's continuity. That's a kind of immortality. Not all stars are constant. Some change. They breathe. They pulse. They flare. They dim and brighten in rhythms that can teach us about the nature of stars themselves. Remember Henrietta Leavitt and her Cepheid variables? Let's understand what those stars actually are. A Cepheid variable is a star that has exhausted the hydrogen in its core and begun fusing helium. It's in a relatively unstable phase of its life. The star expands and contracts, and as it does, its brightness changes. Here's how it works. When the star contracts, it heats up. The increased temperature causes the gas to become more opaque to radiation. light from the core gets trapped, building up pressure. Eventually, this pressure pushes the outer layers outward. The star expands. But as it expands, it cools. The cooler gas becomes more transparent. Radiation escapes more easily. The pressure drops. Gravity pulls the outer layers back inward. The star contracts again. And the cycle repeats, over and over, like a heartbeat, like breathing. The star is literally pulsing, growing brighter and dimmer, larger and smaller, hotter and cooler, in a regular rhythm that can last for millions of years. Some Cepheids pulse every few days, some every few weeks. The period is incredibly regular as any clock, and it's directly related to the star's intrinsic brightness. These stars are lighthouses, beacons with a known luminosity, and because we know how bright they really are, we can use them to measure distances across the universe. Henrietta Leavitt discovered this relationship by examining Cepheids and the Magellanic Clouds, two small satellite galaxies of the Milky Way. She didn't know she was looking at other galaxies. The nature of spiral nebulae was still debated. But she could see that within a single population of stars, the large Magellanic Cloud or the small Magellanic Cloud, there was a clear relationship between period and brightness. Brighter Cepheids pulsed more slowly, dimmer ones pulsed faster. The relationship was precise. This is the kind of discovery that changes everything. A key that unlocks doors we didn't even know existed. Music continues, perhaps adding a subtle pulse to mirror the Cepheid pulsations. Other stars vary in different ways. There are eclipsing binaries, pairs of stars whose orbital plane happens to align with our line of sight. As one star passes in front of the other, the combined brightness drops. Then it rises again. Then, half an orbit later, the other star passes in front and the brightness drops again. By studying these eclipses, we can learn about the sizes of the stars, their temperatures, their masses. There are RR Lyrae variables, older, less massive stars that pulse like Cepheids, but with shorter periods. They're common in globular clusters, those ancient spherical collections of hundreds of thousands of stars that orbit in the halo of our galaxy. There are Mira variables, cool red giants that vary in brightness by factors of hundreds, pulsing with periods of months or years, so extreme that they shed mass into space, surrounded by shells of dust and gas. There are T Tauri variables, young stars, still contracting toward the main sequence, still surrounded by disks of gas and dust from which planets might form. Their brightness changes irregularly as clumps of material fall onto the star, as the star's magnetic field channels hot gas in complex patterns. And then, there are the explosive variables, the cataclysmic variables, the stars that don't just change gradually, but erupt. Music takes on a slightly more dramatic quality, though still maintaining its soothing undertone. Imagine a white dwarf in a binary system with a normal star. The white dwarf, remember, is the dense core of a dead star, about the size of Earth but with a mass comparable to the Sun. If the two stars are close enough, gas from the normal star can be pulled by gravity toward the white dwarf. It doesn't fall directly onto the white dwarf, instead it goes into orbit, forming a disk, an accretion disk, that gradually spirals inward. As the gas spirals inward, it heats up from friction. The inner parts of the disk become incredibly hot, glowing in ultraviolet and even X-rays. Eventually, the gas reaches the surface of the white dwarf, and it accumulates, compressed by the white dwarf's intense gravity, heated by the white dwarf's residual warmth, getting denser, hotter, more and more material piling up, until finally, it reaches a critical point. the temperature and pressure at the bottom of this layer of accreted hydrogen become high enough for nuclear fusion to begin. But this isn't the controlled fusion in the core of a normal star held in equilibrium by the balance between gravity and pressure. This is runaway fusion, an explosion, a nova. For a few days or weeks, the white dwarf and its companion might brighten by tens of thousands of times. A new star appears in the sky. That's what nova means, new. Except, it's not new. It's old. It's a dead star, briefly reignited by stolen fuel. And it happens again and again. Some novae recur every few years or decades. Some have only been seen to erupt once, but probably will do so again given enough time. The white dwarf survives. It's too dense to be disrupted by the explosion. The outer layers of accreted material are blown off into space, but the white dwarf remains, still accreting material from its companion, building toward the next explosion. It's a cycle. Birth and death and rebirth, on a stellar scale. But there's a limit. If a white dwarf accretes too much mass, if it approaches 1.4 times the mass of the Sun, a limit called the Chandrasekhar limit, after the astrophysicist who calculated it, something catastrophic happens. At this mass, the white dwarf can no longer support itself against gravity. Remember, a white dwarf is held up by electron degeneracy pressure, the quantum mechanical principle that no two electrons can occupy the same state, but there's a limit to how much mass this pressure can support. When that limit is reached, the white dwarf collapses. The collapse triggers runaway fusion of the carbon and oxygen that make up the white dwarf. The entire star, Earth-sized but as massive as the Sun, undergoes nuclear fusion in a matter of seconds. The star explodes, completely, utterly, nothing remains. This is a Type 1a supernova. And because all Type 1a supernovae involve white dwarfs exploding at approximately the same mass, they all have approximately the same intrinsic brightness. They're standardizable candles, bright enough to be seen across billions of light years, consistent enough to be used to measure distances to remote galaxies. In the 1990s, two teams of astronomers used Type 1a supernovae to measure the expansion rate of the universe at different times in cosmic history. They expected to find that the expansion was slowing down, decelerated by gravity. They found the opposite. The expansion is speeding up, accelerating, driven by something we call dark energy, a mysterious component that makes up about 68% of the universe and whose nature we don't understand. This discovery won the Nobel Prize in Physics in 2011. And it came from watching stars explode, from cataloging distant supernovae, from measuring the brightness of stellar cataclysms billions of light years away. The universe is strange. The stars keep teaching us just how strange. Here's something to help you rest. Variability isn't chaos. It's rhythm. Those pulsing stars aren't random. They follow mathematical laws. They're predictable. You could set a clock by them. In fact, we do. We use them as clocks, as distance markers, as tools to understand the universe. The explosions, the novae, the supernovae, they seem violent, destructive. And they are. But they're also creative. They're how the universe distributes elements, how it enriches the interstellar medium with the raw materials for new stars, new planets, new life. Death feeds life. Ending feeds beginning. The cycle continues. And on the timescales that matter to you, to your life, to your day-to-day existence, the stars are constant, reliable, there. The sun will rise tomorrow. It always does. It's been doing it for billions of years. It will continue doing it long after you're gone. That's not depressing. That's liberating. Let's venture now into the truly strange, into stellar phenomena so exotic, so far removed from everyday experience, that they stretch the imagination. Let's talk about neutron stars. We mentioned them briefly before, the collapsed cores of massive stars held up by neutron degeneracy pressure. But we didn't really explore what they are, what it would mean to visit one, if such a thing were possible. A neutron star is typically about 20 kilometers in diameter, a city-sized sphere. But it contains about 1.4 times the mass of the Sun. The density is beyond comprehension. A teaspoon of neutron star material would weigh about 1 billion tons, more than Mount Everest, in a teaspoon. The surface gravity is about 200 billion times stronger than Earth's. If you could somehow stand on a neutron star, you couldn't, you'd be instantly crushed. You would weigh as much as a large mountain weighs on Earth. The magnetic field can be trillions of times stronger than Earth's, strong enough to distort the shapes of atoms, strong enough to make the vacuum itself behave strangely, becoming birefringent, splitting light into different polarizations. And many neutron stars spin fast, incredibly fast. The fastest known pulsar, PSR J1748-2446 AD, rotates 716 times per second. The surface of this star is moving at about 24% of the speed of light. Imagine that, a sphere the size of a city with the mass of the Sun rotating more than 700 times every second. The physics involved is so extreme that it tests the limits of our understanding of matter itself. We call these rapidly spinning neutron stars pulsars, because from Earth we see pulses of radio waves, and sometimes visible light or X-rays, as the neutron star's magnetic field sweeps past us like a lighthouse beam. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, a graduate student at Cambridge University. She was analyzing data from a radio telescope when she noticed something odd, a regular signal, pulsing every 1.3373 seconds. At first, she and her advisor, Anthony Hewish, half-jokingly called it LGM1, for Little Green Men, because the signal was so regular it seemed artificial. But it wasn't artificial. It was natural. It was a neutron star, spinning and beaming radio waves into space with clockwork precision. More pulsars were quickly discovered, each with its own period, its own rhythm, some pulsing many times per second, some taking several seconds between pulses. The regularity is astonishing. Pulsars are among the most accurate clocks in the universe. Some are more accurate than atomic clocks on Earth. In 1974, the Nobel Prize in Physics was awarded for the discovery of pulsars. It went to Anthony Hewish and Martin Ryle. Jocelyn Bell Burnell, who actually discovered the first pulsar, who did the work of analyzing the data and recognizing its significance, didn't share the prize. This was controversial then. It remains controversial now. Bell Burnell has been gracious about it, noting that she was a graduate student at the time and that Nobel Prizes often go to advisors rather than students. But still, she made one of the most important astronomical discoveries of the 20th century. She identified an entirely new type of astronomical object. She expanded our understanding of the universe. History remembers. Even if the Nobel Committee didn't properly recognize her at the time, we recognize her now. Her name is spoken with respect and admiration by astronomers around the world. The universe revealed its secrets to her, and she listened. But neutron stars aren't the strangest things out there. There are magnetars, neutron stars with magnetic fields even stronger than typical pulsars. A magnetar's magnetic field can be 1,000 times stronger than a normal neutron star's, strong enough that the crust of the star can crack under magnetic stress, causing starquakes that release more energy in 1/10 of a second than the sun releases in a year. There are black holes, objects so dense that space-time itself is curved into a trap from which nothing, not even light, can escape. We've now imaged the shadows of supermassive black holes at the centers of galaxies. We've detected the gravitational waves from merging black holes. We've confirmed that these impossible-seeming objects, predicted by Einstein's equations, actually exist. There are gamma-ray bursts, the most energetic explosions in the universe since the Big Bang. For a few seconds or minutes, a gamma-ray burst can outshine the entire rest of the universe in gamma rays. They're thought to be produced by the most extreme supernovae or by the merger of two neutron stars. They're so bright that if one occurred within a few thousand light-years of Earth, pointed in our direction, it could cause a mass extinction. Fortunately, they're rare. And space is big. The chances of Earth being threatened by a gamma-ray burst are extremely small, but they exist. Out there, in the vastness of space, these titanic explosions are occurring. Stars are dying in the most violent ways imaginable. Black holes are colliding. Magnetars are crackling with magnetic energy. The universe is far more dynamic, far more energetic, far more strange than the peaceful static dome of stars suggest when you look up on a quiet night. But here's the thing. All of that violence, all of that strangeness, all of those extreme physics are far away. The nearest black hole is about 1,500 light-years away. The nearest neutron star is about 400 light-years away. The nearest star that might go supernova in the astronomically near future, Betelgeuse, which has been acting strangely in recent years, is about 550 light-years away. Far enough that when it does explode, it will be safe. Spectacular, yes. Visible in daylight, probably. But not dangerous. We live in a quiet neighborhood, a safe suburb of the galaxy. Our sun is stable. Our orbit is nearly circular. We're not near any massive stars about to explode. We're not near the chaotic center of the galaxy. We're in a good place. A calm place. A place where life can exist and persist and evolve and become conscious, and that's not an accident. Life needs stability. It needs billions of years of relatively consistent conditions. It needs a star that doesn't vary wildly in brightness. It needs an orbit that stays in the habitable zone. It needs time. And we've had that time. We've had 4 billion years of relative peace and stability, 4 billion years for life to go from single cells to multicellular organisms, to intelligence, to consciousness, to civilization, to space telescopes that can see the echoes of the Big Bang themselves. We're lucky. We're in the right place at the right time. We're in a universe that's old enough to have formed heavy elements, but young enough to still have stars. We're around a star that's stable and long-lived. We're on a planet that's just the right size, just the right distance, with just the right kind of atmosphere. The cosmic lottery has been won. And here we are. For most of human history, we knew of exactly one planetary system. Ours. The Sun and its planets. Mercury, Venus, Earth, Mars, Jupiter, Saturn, and the outer planets discovered more recently. We suspected there might be planets around other stars. It seemed reasonable. Why would our sun be special? But we couldn't prove it. Planets are small and dim compared to stars. Even our most powerful telescopes couldn't see them directly. Then, in 1992, everything changed. Two radio astronomers, Alexander Walshchan and Dale Frail, announced the discovery of planets orbiting a pulsar. Not a normal star, but a neutron star. The planets were detected by tiny variations in the timing of the pulsar's pulses, the gravitational influence of orbiting planets causing the pulsar to wobble slightly. It was strange, unexpected. Planets around a neutron star? How did they survive the supernova that created the neutron star? Or did they form afterward, from the debris of the explosion? We still don't fully know, but the planets are there. We can detect them. We can measure their masses and orbits. Then, in 1995, came the first confirmed planet around a normal Sun-like star, 51 Pegasi b, discovered by Michel Mayor and Didier Queloz. This discovery would eventually earn them the Nobel Prize in Physics in 2019. The discovery method was different from the pulsar planets. Mayor and Queloz used the Doppler method, watching for tiny shifts in the star's spectrum as it wobbles in response to an orbiting planet. When the star moves toward us, its light is blue shifted. When it moves away, its light is red shifted. The size and period of these shifts tell us about the planet's mass and orbit. 51 Pegasi b was bizarre. A Jupiter-mass planet orbiting its star every 4.2 days, much closer than Mercury orbits our sun. Such a planet shouldn't exist according to our theories of planet formation. But it does exist. Nature doesn't care about our theories. Nature does what nature does, and we have to update our theories to match. Music continues, perhaps adding more layers, suggesting the diversity of exoplanets. Since then, we've discovered thousands of exoplanets. Thousands! Using multiple methods, the Doppler technique, the transit method, watching for the tiny dimming when a planet passes in front of its star, direct imaging, actually photographing planets using advanced telescopes and coronagraphs, gravitational microlensing using the gravitational field of a star and its planets to magnify the light from a more distant star, and others. The diversity is staggering. There are hot Jupiters, gas giants orbiting very close to their stars, heated to thousands of degrees, some of which are evaporating, trailing tails of gas as they orbit. There are super-Earths, rocky planets larger than Earth but smaller than Neptune, a type of planet that doesn't exist in our solar system, but seems to be common elsewhere. There are mini Neptunes, planets with thick atmospheres of hydrogen and helium, intermediate between rocky planets and gas giants. There are planets orbiting binary stars, seeing two suns in their sky like Tatooine from Star Wars. There are planets orbiting in the habitable zones of their stars, the orbital distance where liquid water could exist on the surface. There are planets around red dwarf stars, the most common type of star in the galaxy. There are planets around sun-like stars. There are planets around massive stars. There are even planets around white dwarfs and neutron stars. Planets, it turns out, are everywhere. Almost every star has planets. On average, every star in the Milky Way galaxy probably has at least one planet. That means there are hundreds of billions of planets in our galaxy alone. And there are hundreds of billions of galaxies in the observable universe. The number of planets in the universe is almost unimaginable. Trillions, quadrillions, maybe more. A contemplative pause in the music. Here's a relaxing thought. you're not alone. Not in the sense that we've confirmed alien life, we haven't, not yet, but in the sense that Earth isn't unique. Earth isn't special. Earth is one of countless planets, orbiting one of countless stars, in one of countless galaxies. Whatever happened here, the formation of a rocky planet in the habitable zone, the emergence of liquid water, the origin of life, the evolution of complexity, all of that can happen elsewhere. Must happen elsewhere given the sheer number of opportunities. We don't know how common life is. Maybe it's everywhere. Maybe it's rare. Maybe we're the only intelligent life in the galaxy, or even in the observable universe. Or maybe the galaxy is teeming with life and we just haven't found it yet, or it hasn't found us. But the potential is there. The stage is set. The ingredients exist. Somewhere out there, around another star, there might be another world, another ocean, another beach where waves lap against a shore, another organism looking up at its night sky and wondering, are we alone? And you're here on Earth, looking up at your night sky, wondering the same thing. You're connected to that hypothetical being, not in communication or proximity, but by shared curiosity, by the shared experience of being alive and aware in a vast universe, by the shared act of looking up and wondering. That's beautiful. That's profound. We might be separated by light years or by time. Maybe they lived billions of years ago, or will live billions of years in the future. Maybe we'll never meet. Maybe we'll never even know each other exists. But we're both here, both part of this universe, both asking the same questions. You're not alone in wondering. You never were.
Let's talk about what stars give us. Not metaphorically, but literally. What do stars provide to the universe? The obvious answer is light. Stars are the primary source of light in the universe. Without stars, the universe would be dark. Not dark like a moonless night, dark like nothing you've ever experienced. True, absolute darkness, broken only by the faint glow of the cosmic microwave background, the leftover radiation from the Big Bang, now cooled to just 2.7 degrees above absolute zero. But stars don't just provide light. They provide energy, structure, complexity. Think about it. After the Big Bang, the universe was almost perfectly uniform. Just hydrogen and helium gas spread almost evenly through space. Tiny density fluctuations, quantum fluctuations from the earliest moments of the universe, inflated to cosmic scales, were the only irregularities. Then gravity went to work. Denser regions attracted more matter. They became denser still. Eventually, they became dense enough for stars to form. And stars changed everything. Stars create elements. They fuse hydrogen into helium, helium into carbon and oxygen, carbon into heavier elements. They enrich the universe with the raw materials for planets, for chemistry, for life. Stars create structure. Their radiation pushes on gas and dust, creating bubbles and shells and complex shapes. Supernova explosions create shock waves that compress nearby gas clouds, triggering new rounds of star formation. Stellar winds and radiation sculpt the interstellar medium into intricate patterns. Stars create contrast, bright and dark, hot and cold, dense and diffuse. Without stars, the universe would be bland, homogeneous, dead. With stars, the universe is alive, complex, beautiful. And think about what starlight does when it reaches a planet. It warms the surface. It drives weather. It powers photosynthesis. It enables vision. Every plant on Earth is a machine for capturing starlight,
our star's light, the sun's light, and converting it into chemical energy. Every food chain on Earth starts with photosynthesis or with chemical energy from the Earth's interior, in deep sea vents, for example. But for the vast majority of life on Earth, it all starts with sunlight. You ate today, probably. Whatever you ate, its energy came from the sun. If you ate plants, that's direct. If you ate animals, those animals ate plants or ate animals that ate plants. The energy flows from the sun to plants to animals to you. You're solar powered, indirectly, but truly. The calories you burn to think, to move, to live, they came from the sun. And not just the energy, the warmth you feel on a sunny day, the brightness that lets you see, the vitamin D your skin synthesizes when exposed to sunlight, the circadian rhythms that regulate your sleep, tuned to the cycle of day and night. You're adapted to starlight, shaped by it, dependent on it. Your eyes, the most complex organs you have, the ones you're using to read this if you're reading rather than listening, they evolved to detect light. Specifically to detect the wavelengths of light that the sun emits most strongly and that pass through Earth's atmosphere most easily. Your eyes are tuned to a star. Not just any star, but your star, the sun. If you lived on a planet around a red dwarf star, which emits most of its light in the red and infrared, your eyes might be tuned differently. You might see well into the infrared, while the blue end of the spectrum might be invisible to you. If you lived on a planet around a hot blue star, you might see well into the ultraviolet. Life adapts to the light it receives. Life is shaped by its star. Here's something that might comfort you as you drift toward sleep. You're always in starlight. Even at night, even indoors, even underground, you're being touched by starlight. Not current starlight from nearby stars that's blocked by the Earth or by walls, but ancient starlight. The cosmic microwave background, that faint glow from the Big Bang, is everywhere. It passes through walls, through the Earth itself. You're bathed in it, constantly. It's light from the earliest moment of the universe that we can observe, from about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. That light has been traveling for 13.8 billion years. It's been redshifted by the expansion of the universe from visible light to microwaves. But it's still light, still photons, still the universe touching you. And during the day, if you're outside or near a window, you're in the sun's light. Direct or indirect, you're receiving energy from the ongoing nuclear fusion in the sun's core, energy that was released as photons maybe 100,000 years ago, and that has been gradually working its way out of the sun, bouncing from atom to atom until it finally reached the surface and shot off into space 8 minutes ago. You're connected to the sun, physically, actually, by a continuous stream of photons that carry energy and momentum from the sun to you. And at night, if you can see the stars, you're receiving light from dozens or hundreds of other suns. The light left them years or decades or centuries ago, traveled across the emptiness of space, passed through Earth's atmosphere, and reached your eye. The universe is touching you, constantly, always. You're not separate from it. You're part of it. You're in it, and it's in you. That's not mysticism. That's physics. That's reality. And it's beautiful.